For those that you don't know her, Hélène has a background in as a biomedical engineer from the National Polytechnic Institute of Grenoble. And then she did a PhD thesis as Erasmus Mundus joint doctorate in between the Research Center in Oncology and Immunology in Nantes, and the Center of Education in France, and the Center of Education and Research Macromolecules in Belgium. And she joined us in 2019, our section funded by the FNS project dedicated to the advanced imaging methods for quantitative image analysis of the fetal brain. I have to say that she's a really rigorous scientist and very versatile. She has been tackling different aspects more from MRI physics and acquisition towards the image analysis. And now she will expand as well. Soon she will move to another group together with Professor Jalescu and Professor Hackman, that you will not be very far. So I hope we will be able to continue collaborating. And yeah, the floor is yours.
Good morning, everyone, and thank you, Mary, for the kind introduction. So you probably all have heard about this theory according to which the person you are today would be impacted by what happened when you were only a bunch of cells or a beating heart in your mother's womb. So this fetal programming hypothesis states that insults that you may have experienced in utero, such as exposure to alcohol, drugs, or stress, or hormone disruptors, may impact your health later in life and lead to neurological disorders, which makes it worth to study early brain development, don't you think? So by early brain development here, I mean not only the brain after the birth, but also before, like in utero. And such a better knowledge of early brain development will help to improve the evaluation of pregnancy, to support diagnosis and prognosis, also to link prenatal and postnatal evaluation, and to improve postnatal management. But also from a perspective more in neuroscience, this understanding of in utero brain maturation will help to identify new biomarkers of the onsets of such neurological disorders. So neuroimaging is a powerful tool to support this fetal programming hypothesis. For the past decades, it has especially magnetic resonance imaging, thanks to its non-invasiveness, excellent soft tissue contrast, and high spatial resolution. For the past decades, MRI has pushed the boundaries, and in adults, but also in young infants, and even in extremely preterm newborns. So this allowed to reach high quality 3D images, which then allow to perform some quantitative analysis, especially segmentation of the brain, feature extraction, etc. However, the brain not only changes in size and shape, but also quite quickly in relaxometric parameters, which makes quantitative MRI a very promising tool to study brain maturation. So even if those techniques are already used and explored in pediatric populations, still when it comes to fetuses, challenges remain. So first, when you think about a fetus, you think about motion. So contrary to a beating heart, which will beat periodically, we hope, the motion of the fetus is unpredictable. So you need to acquire fast to avoid motion artifacts. Also, we are exposed to low signal-to-noise ratio because the coil is quite far from the image from the organ to be imaged, which requires thick slices. So one option is to acquire 2D low-resolution series of the fetal brain. And here, by low resolution, I just want to make clear that the images are indeed low resolution through plane because of the thick slices. But in fact, in plane, we have a quite nice resolution of around 1 millimeter isotropic at 1.5T, or even doubled at 3T. So in clinical routine, the clinicians acquire T2-weighted single-shot fast spin-echo sequences. So in practice, they acquire at least 3 orthogonal series of 2D thick slices in around, so one series in around 30 seconds. Now, we have also to take into account that the structures we image are very small. So we would like to go to 3D to avoid partial volume effects. However, 3D imaging, 3D sequences are very time consuming. So one way to circumvent this is to use super resolution reconstruction techniques. So this basically means to combine multiple low resolution orthogonal series that are corrected by motion to align them into a super resolution space and to take advantage of the redundancy between the orthogonal series to finally reconstruct a high resolution, a 3D isotropic high resolution volume. So this is based on the classical formulation of an inverse problem with a data fidelity term and a spatial regularization. However, we still have remaining challenges. So first, MRI is not the gold standard technique for to monitor the fetal growth. So only a few centers are specialized into a fetal MRI, and it requires very trained, experienced MR technologists. So this makes data very scarce. Also, we don't have standardized protocols from one center to the other. So here you can see the discrepancies in the image between between two MR vendors, but also for the same MR vendors at different magnetic fields. So data scarcity and the absence of standardized protocol make it very difficult to validate post-processing tools. Also because we lack, and I guess we will always lack, a ground truth. And that's why we need a controlled environment, because if we want to evaluate our strategies, we need to know what we want to achieve. And here comes FaBiAN, so Fetal Brain, the first prototype of a fetal brain magnetic resonance acquisition numerical phantom. As you can see in this overview, here we really want to simulate as closely as possible the MR acquisition scheme of the single-shot fast spin-echo sequence. And this is why I would first like to dig a bit more into the MR physics. So as Oscar was mentioning, the spin-echo sequence is one of the basic sequence in MRI. So it basically consists of a 90-degree RF excitation pulse, followed by a 180-degree refocusing pulse. Then you select the slice you want to acquire, you select the line of K-space you want to sample, and during readout, you record your echo, and you wait for a given repetition time before starting again. So in that case, one line of K-space is acquired within one repetition time, which can lead to very prohibitive acquisition time, especially in fetal brain MRI. So one way of accelerating this is to resort to fast spin-echo sequences. So in that case, from one 90-degree RF excitation pulse, you sample several lines of K-space using several refocusing pulses. And in this sense, you manage to accelerate the acquisition of K-space. So for instance, here we acquire n segments of K-space. So we manage to reduce the acquisition time, the total acquisition time by n. But then, why not acquiring the whole K-space within only one excitation pulse? And this is what we actually do in fetal brain MRI. So we use this single shot fast echo sequence, single shot because we use only 190-degree pulse to acquire the entire case space. And thanks to this method, we managed to acquire one series of 2D thick slices in around 30 seconds. So now that you know a bit more about this specific sequence, let's have a look at how fetal is implemented. So first we need a model of the fetal brain anatomy. So for this, we use segmented high-resolution anatomical images, which allow to change the anatomy, so either healthy or pathological subjects, but also the gestational age. Then we need to kind of convert this anatomical information into MR contrast. So for this, because we lack ground truth measurements in the fetal brain, we need to first merge the different anatomical structures into classes. So here, gray matter, white matter, and cerebrospinal fluid. Then we convert this anatomical information into T1 and T2 relaxation times. And from there, we can use extended phase graph, the extended phase graph concept, to simulate the T2 decay in every voxel. So at that point, we have a 4D matrix that combines the 3D anatomical information over the brain plus the T2 decay in every voxel. Then, by a Fourier transform, we can we get as many frequency domains as we have sampling time points on this curve, and this will help us to sample the case space of the data we want to simulate. So for this, every frequency domain will, at most one line in every of these frequency domains will be used to sample our case space, with the central line corresponding to the frequency domain of the effective echo time. Then this is a partial Fourier technique, so we only need a bit more than half of case space, and then we can recover the other half using the properties of Hermitian symmetry. So if I want to sum up from the fetal brain model, we use this, we merge structures into gray matter, white matter, and cerebrospinal fluid. We convert this anatomical information to MR contrast. Then we use EPG simulations to simulate the T2 decay in every voxel. And now we have our case space. There we add random rigid motion, so 3D independent rotation and translation in every direction. And also we add some random Gaussian noise, again still in case space. And then using a 2D inverse Fourier transform, we can recover our simulated images. This pipeline is currently implemented in MATLAB, and using a cluster, we can get such simulated images in around 10 minutes. So this framework is flexible in the sense that it was really thought so that the user can easily change the acquisition parameters, so in terms of contrast, geometry, and resolution, but also the settings. So the fetal brain model, the gestational age, the amplitude of rigid motion, and the level of noise. So here you can appreciate first results of these simulations. So you have columns corresponding to 4 different subjects at different gestational ages. And every time you have on the left the clinical data, and then highlighted with dots the simulated images. And one maybe striking thing is that weird pattern somehow, but that we find also in the clinical data, which actually shows that we simulate accurately motion, and this is due to the interleaved acquisition scheme. So we showed many of these images to our collaborators at CHUV, and we asked them for feedback about these images. So they reported a good contrast between gray and white matter, a good signal-to-noise ratio. They could visualize the main anatomical structure and also monitor normal gyrations throughout gestation. However, they reported that it was difficult to observe small fractions, so the cortical ribbon was pixelated, and finally that white matter looks too homogeneous and uniform over gestation. But this is not a surprise. First, because here the model we used was an atlas. So this atlas, as any atlas is smooth, it smoothens subtle inter-individual heterogeneities, but also this white matter homogeneity is due to the lack of reference T1 and T2 values. Because as a reminder, we use only one average reference T1 and T2 value for one tissue class and over gestation. So this led us to try to implement this first prototype by increasing white matter heterogeneities. So how do we do this? So first we want to segment white matter into 3 classes to account for hydrated white matter, but also dense fiber bundles that appear during myelination. So we segment white matter into 3 classes using FastFSL. And then from we subtract the intermediate white matter class and the hydrated white matter to get a positive reward map. And in the same way, the dense fiber bundles with the intermediate white matter to get a negative reward map. And these maps will help to modulate T1 and T2 values to account for local variations. So here you can see an example of a subject of 28 weeks of gestation, and you can already see some heterogeneities into the white matter tissue. However, white matter also changes across maturation. The appearance of white matter changes across maturation. So as you can see here, you have the standard deviation of white matter intensity throughout gestational age for normative spatial-temporal MRI atlas of the developing fetal brain. So you can really appreciate how white matter changes during gestation. And we use this variation, we transpose it somehow to compute a control value, which will help us to modulate the T1 and T2 values, not only locally, but now throughout gestation. So this leads to the following results. So you have the T1 and T2 maps computed in the fetal brain, in the white matter mask, sorry, based on the based on the white matter segmentations into 3 classes, sorry, and then you can see the results in the simulated T2 weighted images. So in that sense, we can simulate not only local variations within white matter tissues, but also throughout maturation. Here you can see a first comparison. So for 3 different subjects, you have the simulations using the first version of the pipeline and the second version compared to real clinical acquisitions. And again, you can appreciate the white matter heterogeneities in the second version of the pipeline. So far I showed you mostly qualitative results, but we wanted to go for more quantitative metrics. So we computed the mutual information between super resolution reconstructions from simulated data and real clinical acquisitions. So why mutual information? Because it is an index metric of similarity between images. So meaning the higher the mutual information, the closer the images. And here you can see in green the mutual information corresponding to the super resolution reconstruction from the simulations by the second version. And you can see that it increases at later gestational ages, while the other one for the first version decreases. So another way to show, to look at these results is to have a look at the mutual information between both simulations. And here you can see that the further we advance in gestation, the higher the simulations differ. So meaning that our hypothesis to say that increasing white matter heterogeneities help us to simulate more realistic data is accurate. So now I would like to give you a brief overview of the applications of FaBiAN, coming back to the three main fields I defined earlier. So advanced 3D, high-quality 3D imaging using super-resolution reconstruction, qualitative analysis in the context of segmentation, and finally, quantitative MRI. So one way of using FaBiAN, as it is a controlled environment, is to simulate a ground truth. So an image we will probably never have in fetal imaging is a high-resolution, 3D isotropic high-resolution image of the fetal brain. So in the same way we can simulate 2D low-resolution series of the fetal brain, we can also simulate a 3D high-resolution reference image of the fetal brain. So this is what you can see here. And this image will be used as a reference to compare the results of our super-resolution reconstruction pipeline. So here in this study, we used two different super-resolution pipelines, MIAL and NIFT-IMIC, and we ran a large set of super-resolution reconstructions for different regularization settings. And you can see, so each technique has a default hyperparameter, which was determined empirically. And here you can appreciate the difference between what we use generally as a default parameter and the one that was determined as optimal by maximizing the peak signal-to-noise ratio between the super-resolution reconstruction and the simulated high-resolution reference. So in that sense, FaBiAN is a useful tool to optimize super-resolution reconstruction algorithm. Another way to use it is to validate the method and again optimize it. So for instance, here we studied the number of low-resolution series that was more accurate in the presence of low-motion corrupted series. And we can also extend it to different level of noise or also to different resolution ratio. Then, because data in fetal imaging are scarce, FaBiAN is a great playground to simulate as many data as we want at almost no cost, because we just need a fetal brain segmentation, and then we can simulate a bunch of MR sequence parameters. And so here is an example for data augmentation. So you can see the clinical super-resolution reconstruction along with its manual annotations. And here, this is a result of a 2D unit trained on clinical data only. And you can see that it fails, the model fails at accurately segmenting the cortical ribbon. Whereas here we add on top of the clinical data, we add some simulations and to help the network improve the segmentation. And here you can see that actually we managed to better depict the cortex. So if we want to push the limits even further, we can train a network only on simulated data, just to see if our data are realistic enough to kind of fake the model. So here you can see a plot of the dissimilarity coefficients, which measures the segmentation accuracy. And here you have the results for 3D unit trained only on clinical data. And here's the same 3D unit trained only on simulated data. So these simulations were generated using the exact same models as the clinical data, but like here we used really only simulations. And Of course, we did not expect the network to perform as well with simulations as with real clinical data, but still these results look quite promising and are in line with the idea of training a model with many simulations and only a few clinical cases. And finally, another application to FaBiAN is the evaluation of new quantitative MRI strategies. So for instance, in the context of T2 mapping, because again, we have a controlled environment with a known motion, and we can compare our results with a high resolution reference image. So just briefly, as a conclusion, FaBiAN is a general, realistic, and flexible framework. So general in the sense that it allows to simulate as many, to simulate various MRI acquisition schemes. Realistic because we simulate white matter heterogeneities, and the neuroradiologists were happy with the simulated images, and flexible in the sense that we really allow the user to change the ML sequence parameters to their clinical scenario. It was used as a controlled environment to provide a ground truth for the evaluation of post-processing techniques, for data augmentation and transfer learning, and also for the exploration of new T2 mapping strategies. And some upcoming extensions are envisioned. So translating FaBiAN from clinical field to low field ML systems, and also extending it to other populations, so here newborns. And this is part of the new Swiss National Science Foundation project of Mary. And since it is probably my last presentation in the context of CIBM, I would like to take this opportunity to thank Mary for her support during this past 4 years already, to thank all my collaborators and colleagues and collaborators at the Department of Radiology. And yeah, you can see that many people were involved in this project, and also the Swiss National Science Foundation and the Protechno Foundation. Thank you for your attention.
Questions, comments from the audience?
In slide, yeah.
Yes, fine.
So presentation, but in slide 35. Whoa.
Specific.
No, it's just like, why do you have two lobes in here instead of? I mean, you have the clinical and the simulated one, but why do you have two lobes?
Yeah, sorry, I didn't go into this because you have the neuro, like the healthy subjects and the pathological ones.
Ah, okay, thank you.
Have more questions? Go ahead.
Yeah, thank you for very interesting studies. Is there any separate guideline for this fetus? Is that usually this work, this fast pinnacle is a lot of 180 process, so SAR issues sometimes we are concerned about that. And so you acquire entire case, but not actually entire, but it's a but it's a fetal imaging. So any different guideline for fetus or some in safety issues in terms of safety issues?
You mean other sequences or?
Just, I don't know, it's an FDA guideline, or we know that SAR guideline there, right?
Yes, for the start, they are quite flexible in the angle of the refocusing pulse, so they can decrease it until 120 degrees, something like this, to reduce the SAR exposition.
Yeah, I think we can do that too. So no guideline for the fetus, independent or separately. Just I'm curious. Okay.
As long as the mother is big and she's on breath hold. In some countries they do some medication, but our experience seems to say that fetus actually moves, so that helps more for the model. But no, I mean, it's the same safety reasons steps that we exhibit.
Yeah, I just wondered this. Okay, thank you.
So
since you're expert also in the thalamus segmentation, I was wondering, look at you take the subcortical region as a whole, right? For the segmentation at the moment.
So just because we lack foreground truth measurements, but one way would be to modulate as well between structures. But this we haven't explored it yet.
So is it from the clinical perspective, it will be interesting to look at this early developmental stage to look at some areas or the sub areas. Will this make any interest for clinical? I was wondering.
From clinical pathologies, I would not know how to answer. But from the neurodevelopmental point of view, yes, of course, I would like to explore this. But we are far from the resolution now to really go into in detail.
So it's even with the super resolution, that would be a challenge.
Yeah, I think so.
Yes. Isn't that some kind of like way of getting data from cases where that both anesthetized or like have to be anesthetized anyway, and then you might as well just make one MRI image and then do that several times? I'm thinking about like some case where that would ethically be okay. And then you can acquire like high resolution, motionless data.
But as Mary was saying, even with anesthesia, you still have you may still encounter motion, and then you really want to minimize the times that you spend in the scanner. I mean, it's supposed to be non-invasive, but still you just use it for like in case of equivocal situations. So I mean, at least in Switzerland, you wouldn't extend a scan just for research purposes.
So thank you very much, and enjoy the coffee and the tea and the breakfast, and have a good summer.